Hello, this is Matt Gaskill, Philosophy 160, for working the presentation for problem 1.18.17. But in this case, we're going to work those problems using various proof methods. You may have seen previously we worked these out with truth tables. So we know the answer is going in. Now the question is, can we prove otherwise? And so what we've done is put together the proofs here on this page, and we'll work through each one. So for the material implication question, whether or not it was associative, we demonstrated with the proof tables that the material implication was not associative. So that one's pretty easy, so we put that one at the top. Now the next one, the conjunction associativity, we used a formal proof method, and to use the formal proof approach, we used the rules of inference and the rules of equivalence. So let's look at those just real briefly so that we can get an idea of what we're talking about here. So with the rules of inference, these take two or more premises in a certain form and then return a particular conclusion. And so, for instance, if we know one of our premises is P only if Q, and if another of our premises is P, then we can be confident that the conclusion is Q. And these need to operate on, if you will, complete premises, complete propositions. So these operate on the dominant operation. So P and Q, they could be anything. They could be a long string of logical arguments, but at the topmost level, that dominant operation, it needs to be in the form that we've shown here in this table. Now we've got a couple of red font arguments, and so these are kind of gotchas. These are actually not valid arguments, but you might be tempted to think that they are. And so if you've got a premise P only if Q and a separate premise saying not P, then you would really you'd like to try to say, well, then not Q is the conclusion. And that actually has a name. It's called denying the antecedent. But it's not a valid argument, so you can't use that argument as much as you might want to. A few of the others, P only if Q. Well, if I know Q, then don't I know P? No, that's considered, it's called affirming the consequent. Again, it's one of those ones that you're tempted to try, but it's not a valid argument. And so you've got the kind of the popular rules of inference here. A lot of them have names: hypothetical syllogism, constructive dilemma, and then what we've done is we've created a shorthand, just kind of a notation for each of these kind of named rules of inference: HSDS, CD, conjugation, introduction, CONG, simplification, addition. And then also we've got rules of equivalence. And so these are represent logically equivalent propositions. So for instance, if I have P, if I know P, I also that's logically equivalent to not P, so it's a double negation. So anywhere where I see P in my argument or in my proposition, I can just replace that with double negation in the front of it. All of these are acceptable equivalence replacements. No red font here. Again, the popular ones have names, and we've given shorthand. Sometimes the shorthand is the same because it kind of applies similar rules. So commutativity of conjunction, disjunction, or material equivalence, we just call them all COM. And so you've got this COM, and pay attention to that one, and also this simplification. And so what you'll see is, or simp, and so what you'll see is we've taken our proofs and we've started out with the premise. The first premise from the question, which was parenthetically A with a connective B, and then all of that connected to C, and we're using the conjunction connective. That's what we're trying to demonstrate, associativity back and forth. And so we start with the premise that they gave us, and what we're trying to derive by the end of our proof is the other form, where we've moved the parentheses to the second set of variables from the first. And using the rules of inference and the rules of equivalence, that's what we do. And so we start out with this premise. We use that rule of simplification, where we can basically drop at the dominant operation, we can drop to the right of that operation of the conjugation. And so we end up with just A and B. And we took that from line 1. So kind of our format is what we are deriving on this line, how we're deriving it, well, what line we're deriving it from, and then how we're deriving it. So we're using simplification of line 1 to derive A and B. Now we go back to line 1 and we use the commutativity rule in order to move the C from the right-hand side over to the left-hand side. And so we're just swapping positions, and we're doing that via COM, and we're doing it on line 1. Now we return to line 2, and we again use simplification, but this time we're chopping off that and B, so we end up with A. So the way simplification works, you only get to chop off the right-hand side, and you keep the left-hand side. So we're going to want to get B by itself, and so what we're doing is going back to line 2, and we're going to swap A and B using the COM rule. We're going to go back to 3. We're going to use the simplification rule to chop off everything to the right of the conjunction, end up with C. We're going to go back to line 5, and we're going to chop off the and A and end up with B using simplification. And then we're going to use conjugation to put together these two lines. So B and C, we're going to use lines 6 and 7 through conjugation. And then we're going to use conjugation again from line 4 to pick up our A, and line 8 to pick up our B and C. And then we end up with that formal, the second statement there. All right, so now what we've proved that we can move in one direction. We can go from the parentheses on the left, and using all of our formal rules of proof, we can arrive with the parentheses on the right. And then what we do is we do a similar approach. We start with the parentheses on the right, and we work our way through until we derive the original form where they're on the left. And so the left and the right columns, we're using the left column to demonstrate that we can derive the conclusion A and both B and C. And then on the right-hand side, we make the other derivation where we derive both A and B together and C. And we need this bidirectionality to illustrate the logical equivalence between the two, and thus that they're associative. So that's our formal proof for associativity of the conjunction. For the inclusive disjunction, the or value, we simply just kind of work it out logically in words. We set one or more variables to true, then both statements are true. So it doesn't matter if it's A, B, or C, 2 of them are true or all 3 of them are true. As long as any of them are true, then the entire statement is true. And then if they're all false, then the entire statement is false. And that's true for both the parentheses on the left and on the right. And so through that kind of logical set of thoughts, that's our proof for inclusive disjunction associativity. Now, in the case of the exclusive disjunction, that one's a little bit tougher because all of our rules of inference and our rules of equivalence, they only operate on conjunction, disjunction, the inclusive disjunction, material equivalence, material consequence, but not, we don't have any formal rules for the exclusive or. And so the only way to work out a formal proof for the exclusive or would be to convert it or expand it into a form that allows those rules to be used. And so two logically equivalent forms of the exclusive or, say if we're looking at P exclusive or Q, then in that case it's P or Q and then and, not P and Q. And we can also look at that as P and not Q or not P and Q. And so the second option seemed to be the most useful for what we wanted to do as far as a formal proof is concerned. And so we went ahead and converted that or expanded using this format into the original problem, the problems where we had A exclusive or B parenthetically and then exclusive or C, and then you end up with the expanded form that looks like that. So it gets to be pretty onerous. And then we work our way through, and then the other version where we've got A exclusive or parenthetically B exclusive or C looks like this second line here. And so then we start working them through a couple of proofs. And so again, like our first proof with conjunction, we try to work one way, and then on the other side of the proof, we would try to work backwards. And so we kind of just work through the first 9 lines using comm and distribution and De Morgan's and lines 1, 2, 3, just working our way down, and it just constantly keeps expanding. And the goal really is to get to a line where everything on that line is identical to everything on a line in the second proof. So that would demonstrate that regardless of which way you were deriving from, you can arrive at the same answer. But you can see it gets to be pretty unwieldy, and so we went ahead and we just kind of called it a day and said it's easier just to do a 16-row truth table than however many lines this proof ends up becoming. And there's just so many opportunities for typographical errors in this that didn't do it. And so another approach is to kind of make that logical case like we did with an inclusive disjunction, where we put together several cases together and see if we can make some concise statements about what might prove that the exclusive disjunction is associative, again without using the truth tables. And so here is that, or an attempt at that. So to consider several similar cases together, when we have exactly one variable that's true, then either the parenthesis within either the value within the parentheses is true, or, and we're using or in the exclusive sense here, the variable outside the parentheses is true. resulting in an overall true value for the statement. And it doesn't matter where those parentheses reside. If all three of the variables are true, then the value within the parentheses would be false, and leaving the true value outside the I'm sorry, yeah, if all of them are true, then the parenthetical value becomes false, and then you have that true by itself outside the parentheses. All right, and in the case where you have exactly two true values that exist, then you have an overall false value for the statement, since either the value within the parentheses is true or the value outside the parentheses is also true, and then vice versa. And so again, it doesn't matter where those parentheses exist in relation to the true and the false values. And so the end of the bottom line is that the two statements are logically equivalent, and so the parentheses are associative. All right, and then in the biconditional proof, we have a similar problem in that we only have really a few rules of equivalence that we can use for that particular operation. And so for the biconditional proof, again, we would have to expand it if we wanted to do a formal proof, and we have those kind of two options for expansion, and we would think it's pretty likely that as we feed those expanded forms back in to the original argument or the question, that we're going to end up with a formal proof very similar kind of in size to the exclusive disjunction. So we went ahead and didn't follow that approach. We just said it was much easier and less error prone to simply just use the truth table versus a formal proof. So that's that was the last one. So hopefully that all made sense to some degree. If you got any questions on the rules of equivalence, rules of inference, or on any of these proofs, please go ahead and hit me up on the Pronto, and we'll see if we can't get things cleared up. All right, thank you very much.